Okay, wonderful. All right. Um, so the title of my talk is Demystifying Data Structures and Algorithms Used by Database Storage Engines, right? But first, who am I, right? So my name is Adewumi Sunkanmi, and I am a senior software engineer at Acronis. So I work primarily on advanced automation, even though as a senior software engineer, I get to work across multiple services, but I work on advanced automation primarily. And some notes about me is that I love to stick to the fundamentals because I believe it all boils down to the fundamentals, actually. All right. So this is the outline of my talk. So basically, we'll be going through an overview of a three-tier application. Then after that, we're going to be looking at the criteria for selecting the best database for an application. And then we're going to be looking at an overview of the database architecture, right? And finally, I'll be comparing and contrasting the different storage engines that we have and the trade-offs that you might need to make when you adopt each of them, okay? So before I continue, can everybody hear me? Can I get a thumbs up if I'm being heard? Okay, wonderful, great. Okay, so you want to build an application, right? So basically, you have a client, then you have a server, right? You have this server that talks to a client. Then you have a database, right? Which is the persistent store that stores the data that you want to store, basically, right? But there is a question that might come to your mind, which is, which database should we use, right? So which is the right database for this particular application, right? So we have Cassandra, we have MongoDB, we have MySQL, we have Postgres, we have Google's Bigtable, we have Neo4j. So many databases you can think about, right? So which specific one is the right one for your application? How do you select the best one for your application? Now, there are some criteria that comes to us outrightly when trying to select the best database for an application, right? So for example, we have the structure of the data we want to store, right? So if the data is highly structured, then you might start thinking of something like, say, a relational database like Postgres or MySQL, right? But if you're storing, let's say, some blobs of JSON or something, you might start thinking of using, say, in maybe MongoDB, right? But if you're storing graph data, so for example, you are storing map information, then you might start thinking of something like Neo4j, right? So, I mean, that's like the first thing that comes to your mind, the structure of the data. Then secondly, you might start thinking of scalability, right? I mean, it is the joy of every company that a product should scale, right? So you want to consider this while selecting your database, right? So you might think of horizontal and versus vertical scaling, right? So does the database allow you to scale horizontally or vertically, right? Do you have to have multiple machines, or you can have a single machine and then increase the capacity of that single machine, right? And another thing you might consider is sharding. And so basically, sharding is partitioning your data across multiple nodes, basically, right? So you have like a typical example would be, taking the longitude and latitude of a user, creating a geohash with that, and using that to find the location to store the user's data, right? So that's like how sharding basically works, right? Then we have replication. So in case you're familiar with MySQL master and slave or MongoDB replica set, where you have one master node, then you have other backups that you sync data across, right? So you might also consider that in your application because that makes your application more available and more redundant, more fault tolerant, right? And one thing that is often considered also is the support, right? So is that database highly supported by the community, right? The more familiar database the developers are with the database, the faster they can probably innovate, right? Okay. So the fourth one, which is my major focus today, right, is that you need to consider the rate of write and read of that application and how exactly these operations are handled at the hardware level, right? So how exactly does the database handle writes and how does the database handle reads, right? So that's something we have to really consider. Most people are not familiar with this. Even the senior developers out there, most of them don't really understand this aspect of the database, right? So that would take me to the database architecture itself, right? So if you can hear me, can you just give me a thumbs up so that we can be together? Okay, great. All right. So we have the rate of write. Okay, so I've explained this. Now, when you look at your database architecturally, this is how it looks, basically, right? This is how your database looks. So you send your query through a protocol, right? And that protocol is actually half duplex, meaning that you can't be receiving and be sending at the same time. You can either be receiving or be sending, right? So you send your query to that protocol. The query goes to a query cache, right? So the query cache checks if you've run that query before, right? So if you've run that query before, it just returns the result, sort of how Redis works, right? Otherwise, it sends out your query to a parser, right? So the parser, converts that your query to a parse tree, right? So this is the form that the computer can understand basically. So it looks something like this, right? So this is how your query will look after the parser sort of makes it a parse tree, right? And the parser does things like, semantic checks. So basically checking tokens if they are correctly, written and stuff like that. Then the parse tree is sent to a preprocessor, right? So the preprocessor does what is called the semantic check, right? So the semantic check basically means that it checks if, for example, if the table you are trying to query exists, or if the column you are trying to query exists, right? So these are like semantic things that the parser cannot do. So that is the work of the preprocessor. Then that parse tree is sent to a query optimizer. So the work of the query optimizer basically is to take your query, right, and figure out the best way to execute it. Most times when we write queries like that, we don't really pay attention to how it's executed, like on the back end. We just care more about the ease of writing the query, right? So it is the work of the query optimizer to figure out the best way to execute that query. And that boils down to things like generating different execution plans and calculating the cost for each, right? So once we have a query execution plan, it is sent to the query execution engine, right? So the query execution engine makes an API call to the storage engine, right? Then the storage engine orchestrates how write and read is done from the disk, right? So if you look closely at this diagram, you will discover that the last component before the hardware is the storage engine, right? And if you also look closely, you will discover that you are talking to this storage engine through an API call. What that means basically is that storage engines are pluggable, right? So you can have a DBMS that uses multiple storage engines. And this is why MongoDB could change their storage engine in 2014. So they changed it to like Red Tiger, right? Because you can change the storage engines as long as they have well-defined API interface. Okay, so now we see that the storage engine is very, very important. So let's look at the storage engine itself. Now, there are two major kinds of storage engines, okay? So we have the log structured match tree storage engine, and then we have the page-oriented or B-tree storage engine. So I will start from the first one, which is the log structured match tree storage engine, or simply LSM tree storage engine, right? So this is the official paper for LSM, right? So in case you have time in your layer time, you can check out this paper. It documents how LSM tree actually works. Okay, so the official definition of LSM tree is that the LSM tree is an immutable disk resident data structure, and it is optimized for sequential writes while maintaining the acceptable read performance. Okay, so basically, what does this mean, right? I like to explain things, not just, give you in words. So let's see what this basically means. So when you think of a log structured match tree storage engine, three things should come to your mind, right? So the first one is the mem table. I will explain what this component means actually. Then we have the in-memory index, and then we have the SS table. Okay, so I would explain these three components as we move on. So let's say you have these writes that you want to make to your database. So you want to write these keys and values to your database, right? So what happens is that the writes are persisted in memory first. So that your write is not going to the disk first, it's going to an in-memory binary slash tree, basically. And in this case, we use the variation of binary slash tree called the red-black tree. And the reason why we are using this is because the red-black tree is self-balancing. So if you sort of understand data structures, like you understand that it is possible to have left skew tree or right skew tree, and that is not nice, basically. So you want to make sure that the tree is height balanced. That is why we are using the red-black tree in this case. So you write we create this tree basically, and once we reach a threshold of, for example, 3 in this case, we send all those writes to the disk. So we call that flushing. So basically, we flush that to the disk. Now, this is very powerful because we are not making a disk IO each time you are writing. We are basically sort of buffering all those you write in the memory in RAM first before writing to the disk, which sort of increase the write throughput, right? Okay, so now I know I said that you have 3. Once you have 3 nodes, you write to the disk. But I mean, in the real sense, hardware is cheap, so why should we not have much more, right? So what we're doing in practice, in real life, is that we specify a capacity, right? So in this case, we say that, okay, once we have 40 megabytes of writes in the RAM, they flush it to the disk, right? So that's what is going to happen. So basically, this SS table file would be something like this. Now, of course, we won't be storing the 40 megabytes like this. Basically, this will be broken down to blocks, right? So we have something like this. So we have 10, 10, 10, 10 megabytes, right? So if you accumulate this together, we have 40 megabytes. So we sort of divide them into blocks. Now, why is this very important? It is important because now we can generate what is called the in-memory index that looks like this, okay? So what is an in-memory index? So an in-memory index in this case, if you understand types of indexing, this is what is called a sparse index, right? Or you can check that out later, but this is a sparse index. So why is this important? So assuming we want to fetch something like, say, APA, we want to fetch APA, right? So we don't have to scan through all the keys, right? Basically, we know that APA exists before ARIC, right? P comes before R in the English language, right? So in the English alphabet, right? And L comes before P. So we basically know that APA will exist in this particular block over here, right? And this byte offset represents the location of that key in the file. So if you are looking for APA, we know that APA would exist in the first block, right? So in this case, we won't be fetching all the sort of 40 megabytes of capacity, right? We'll be fetching just 10 megabytes, which increases the time for disk IO because we are fetching something lesser. I hope that is clear to everyone. Please, can you just give me a thumbs up if you understand what I just said? Can you give me a thumbs up? Okay, great, awesome. Okay, so that is that on the in-memory index, right? Now, of course, this is, we just wrote 3 data, right? So if you check this, we have just 3 entries, right? But we have 6. So what happens if the red-black tree is filled up? What happens, right? So what happens next is that we build a new instance of the red-black tree. And that is what we're doing next, right? So we have this new instance, right? And that also gets persisted to the disk once it reaches 3 nodes. Now, pay attention that we are storing the time that we are storing this file in the disk, right? Pay attention to the fact that we actually, so we have T2 here, right? And we have T1 here. So we are storing the time we are persisting this sort of table to the disk. And also take note that these are sorted, right? And the reason why this data is sorted is because by the time you want to persist it, you can do something like an in-order traversal on the tree that gives you the sorted form of those keys, and then you can persist that in the disk. I hope that is sort of clear. Okay. Now, the next thing here is, let's say that you want to read Ben. So you want to find Ben. So what can you do, basically? So you first check the in-memory tree. Basically, you check the RAM, right? If you can find that particular key there, right? If you can't, then you proceed to the most recent SS table, right? Okay. Then if you can't find it in the most recent SS table, you go to the next recent. So this is like going to the least recent. So you go to T1, right? So you keep going like that until you find the key that you want, right? So that is how find works. Okay. Now, so we've done read, we've done write. How do we undo updates in an LSM tree storage engine? How do we undo updates, right? Now, remember that I said that the first time you encounter this data is when you return it. So basically, when you want to update, you just send that particular key with the most recent value, right? And since we are returning the most recent state of that data, the most recent key that you wrote is what will be returned, right? And that is why we actually had to sort of map the time to each time you sort of flush this to disk. So we can know the most recent state of every key, right? So that is how you undo updates. So in this case, if you want to find Ben, Ben will not be returned from T1, right? Ben will be returned from T2 because T2 is the most recent state of Ben, right? So that is how you handle update. Now, how do you handle delete, right? The same way, basically. It's just that in this case, you won't be sort of mapping the key to any value. You'll be mapping that key to what is called a marker, and that is basically called a tombstone, right? So a tombstone indicates that, okay, we have this key, but it has been deleted, right? So if you try to fetch that key, you'll get the key, basically, but it will be mapped to a deleted marker that, okay, this key has been deleted, right? So that is how we handle delete. Now, if you look at this diagram carefully, you will discover that we have duplicates. So basically, we have Ben here in T1, and we also have Ben in T2. So we are wasting space. Actually, we are basically wasting space. So what can we do? And this is where what is called compaction comes in. So what compaction does is that it takes all these files, all these SS tables, and then it merges them together, right? And while it is merging them together, it checks for duplicates, removes it, right? And then it checks for keys that have been deleted and also removes it. So that's what your compaction does. So your compaction works basically like the way merge sort works, if you understand merge sort from basic data structures and algorithms. So that's how your the compaction basically works, right? And there are multiple kinds of compaction, right? So I recommend you check out Cassandra documentation if you want to know more about how compaction works, okay? Now, so what if we don't find the key? So let's assume you checked the RAM, you didn't find the key, right? You checked T1, you checked T2, sorry, you didn't find the key, right? Then you checked T1, you didn't find the key. So let's assume you have like 1,000 keys. So you have to keep checking each of those SS table, right? And that can be time consuming, okay? So what can we do? Is there a way we can optimize the read, right? That's possible. And this is where Bloom filter basically comes in. So Bloom filter is a separate data structure on its own. And what it does is that it can tell you if a key exists or not. However, it is probabilistic. So for example, if you want to check for a key in this SS table, if the key does not exist, the Bloom filter will tell you no, strict no, and like it doesn't exist truly. But if the key exists, it can tell you yes. But that yes is 99% correct. So you can actually get a yes, but while you check the SS table, you won't find the key, right? But that doesn't happen all the time because it's 99% accurate. And I hope that sort of makes sense. Okay, so now remember that we're actually persisting this data in memory before we flush to disk. And that is dangerous because your RAM is a volatile storage, meaning that if the power goes off, you lose all these entries, you lose all these writes, right? So how can we stop this from happening? So the way LSM tree storage engine handles this is that it has what is called a write ahead log file. So how that works is that before you persist the data in the RAM, you write it to the file, right? So even if a power failure happens, you can always sort of fetch that your write back from the file. So if you understand how something like event sourcing works in system designs, this should be easier, right? So you store those writes in the file. So even if a power failure happens, you can always fetch the state back from that file. And the file is actually persistent, right? It doesn't go away, right? So that is how you handle power failure. So structured mass storage engine is used in Apache Cassandra. We have it in WebTiger. So if you use MongoDB, that is where WebTiger is, right? That's the storage engine behind WebTiger, behind MongoDB. We have InfluxDB, we have the Yugabyte DB, we have the ScalarDB, CockroachDB, Google SpeakTable, RocksDB. So you can actually go to these people's documentation and you can have the fundamental knowledge of how this database or this storage engine works, right? So that is that on log structured mass tree storage engine. Now, types of storage engines, right? So we've looked at the LSM tree storage engine. Now we're going to be looking at the page-oriented storage engine, right? Which is also known as the B-tree storage engine. So this is the official, paper on B-tree. So it is called the Ubiquitous B-tree. It was published in 1972. I wasn't born that time, so I don't know about you, but I wasn't alive that time. And basically, the paper goes into giving different variations of B-trees and how they can be applied. So B-tree are page-oriented indexing structures. I'm going to explain this actually. So some important notes on B-trees. They store key value pairs. They are self-balancing. They are often used for indexing. They are mutable data structures. Basically, you can do in-place updates. Each node is a fixed size block of 4 kilobytes. So a page is the simplest unit of storage. That is a page. I'm going to explain these things. So don't worry, I'm going to go explain these things, okay? Then you can only read or write one page at a time. So that is what you can read multiple pages. You can only pick one page at a time. Now, so let's look at the anatomy of a B tree. So if you check out this B tree here, we have the first root page, and that root page has pointers and keys. Now the pointers points to the ranges of values, right? So in this case, if you check 12 and 30, this pointer here points to values between 12 and 30. So we have 13 to 27, basically, right? And if you also check 30 to 50, we have this range from 37 to 42. So you can see that this is within the range of 30 and 50, right? And also check the inclusivity and the exclusivity. So if you go down here, you can have 30, but you can't have 50, right? So you can include 30, but you can't include 50. You can check out the brackets, like to understand what I'm trying to say. Okay, so that's basically the anatomy, right? So if you look at a page, a single page in disk, right? It looks something like this. Right? I won't go into this, but you can make a research on how this looks basically. But this is how it looks like really. This actually looks. Now, the last page is called the leaf page. That is the leaf, the page at the lowest level, right? And if you check this out, you discover that we are not just storing pointers, but we are also storing pointers and values, right? So we are storing both the pointer and values, right? So this is where the value actually exists. The value does not exist in the other pages. It exists only in the key, right? It exists only in the leaf page, right? Now, another thing to note is branching factor. So what is a branching factor? Basically, a branching factor is the number of pointers in a page, right? So if you check out this particular page here, if you count this, we have 1, 2, 3, 4, 5. So we have 5 pointers. That means this P tree has a branching factor of 5, right? And the depth is also 3. So what is the depth? Basically, the depth is the number of layers, right, that we have. So in this case, we have 3 layers. That is the depth of the B tree, okay? Now let's assume that you want to reach 78, right? So how does that work? So you go to the root page, you check out the first range that you can find. So 78 is between 50 and 120, right? So you go to the pointer between that and check like where that points to, the page that pointer points to, which is this particular page here, right? And then you also check this page, you discover that, okay, now you can find 78 between 69 and 90, right? And then you also go down one layer, right, through this pointer here to this particular page. Now you can see that, okay, 78 is in this page. So basically how that works is that you can fetch all the keys in this page. You can do a binary search because all these keys are sorted, right, to get 78. So if you understand how like data structures and algorithms, basically that should be easy to get, right? Okay, so I've explained that, right? Now let's say that you want to, okay, so actually searching for a key is faster in a B tree. Why? Because you are doing a range scan, right? So you're not sort of looping through all the keys in the database. You are actually doing a range scan before you arrive at this particular key, which is faster, right? So this takes mathematically log n time, right? So that is why B tree is sort of very good when it comes to reading from a database. So if you're trying to build an application where you're going to be doing lots of reads, it is advisable that you go for something like B tree because read is very fast for B trees, right? Okay, so now let's assume you want to insert 87, basically. So you want to insert 87 at the leaf. So what happens is that you check out the leaf and you take note of the branching factor, right? So in this case, the branching factor is 5, and we already have 5 keys, basically. So we have 1, 2, 3, 4, 5. So meaning that if you add this 87, it will exceed the branching factor of this particular leaf page. I hope that makes sense, right? So what you can do, basically, is to split that particular page into two. So basically you generate a new page and then you move the keys in the first page to the next one. So it looks something like this, right? Okay. So now you can see that, okay, you have two pages and you have more spaces, right? And the next thing to do basically is that you have to move the first key in this particular page to the parent page. So that looks something like this, right? So now you have moved 85 to the page above it, right? To the parent page. Now, one question that might come to your mind is, what if the parent page is full? So let's assume that when you inserted, let's assume that this parent page is full and you are trying to insert 85 in that parent page. It won't accommodate it, right? So what you can do is to also split that parent page. So this should give you an idea of how insertion works, right? So it's a bottom-up recursive operation. So you sort of start from the leaf and you keep trying to find the best way to place to insert these keys until you find a free space. So I hope that makes sense. But basically, you go from down up, right? And you keep trying to find the best place to put the key at the new page. So I hope that is not too complicated. All right, so how does update works? So update works simply, in a very simple way. So basically, you fetch the leaf page, right? And when you fetch the leaf page, you can basically update that particular key, the value, right, of that key in the leaf page, and then you write it back. Remember, the only thing you can fetch is a page. A page is the simplest unit of storage, right? So you can't fetch a key, like just the key. You have to first fetch the page, update that key in that page, then write that page back to the disk. So I hope that makes sense because you can only fetch a page, not the particular key, right? Okay. So now let's look at, let's try to compare LSM trees to B trees storage engine, right? So how do they differ and what is their strengths and weaknesses? Now for LSM trees, it is optimized for writes because we are sort of like caching the writes in RAM first before, flushing into the disk. So you can have lots of writes to the RAM, which is faster, right? Your B tree is optimized for reads because you are doing a range scan each time you want to find a key. You're not sort of scanning through all the keys, basically. So B trees are optimized for reads. And also, LSM tree compress better, no fragmentation. For B trees, basically, there is fragmentation, which wastes space. So what does fragmentation mean, right? So if you remember when we splitted this leaf page here, you discover that we have these two empty spaces, right, that we are not using, basically, right? If no one writes to this page for the next 10 years, this particular page would be there. This particular spaces would be empty, right? That is a waste, right? So that is why fragmentation in B-tree is sort of another issue you might want to look into, basically. Then for LSM tree, we have duplicates, right? Remember that we have duplicates in our sort of SS tables before we do compaction. Basically, we have all these duplicates in the SS tables. So that is also in that waste space to some extent, right? Before you do compaction. Now for B trees, key exists only in one place, right? So you can only have one particular key in the leaf page, right? And this is good, right? This is good because now you can lock that particular key. You can say, okay, I don't want any other person to access this key. And that is good for transactions. For those who might understand how transaction works, you begin a transaction and then you commit it, right? And you don't want any other thread to mutate that data while you are performing an update on that particular data, right? So because you have the key only in one place, you can do transactions, right? So that is one place where B-tree storage engine truly shines, right? So if you understand how, maybe you write Golang, if you understand how mutexes works, this should be a bit familiar. Or you understand how isolation level works in MySQL, this should make sense. Okay, now for LSM trees, one drawback basically is that when you have spikes in writes, they can have performance issues. So imagine where you are doing like a Happy New Year, right? So maybe it's 12 a.m. January 1, right? Everybody tweets Happy New Year. And remember that we're actually storing these keys in the memory, right? So you have all this data in memory, right? And then you flush them to the disk, and now you have so many SS tables, right? So many SS tables. So what happens is when compaction wants to happen, you have to compact all these files. So let's assume you have 1 billion files, basically. You have to sort of compile all those files, which can cause a huge performance overhead, actually. Okay, so So that is that on LSM3 and B-tree storage engine. So I hope you sort of you have an idea of the right one to choose for your application if you want to build one. Okay. Now, the last thing I'll be talking about is space optimization in B-trees, right? So before I do this, can you confirm that you can still hear me, please? Okay, wonderful. Interesting. I can get that. Yeah. Now, remember that I said that B-trees are indexing structures, right? So in the first instance, we have this primary index, basically, right? And you have these keys and all, right? Now, this is for primary index. Now, you can also have secondary index, right? So primary index is based on your primary key. So the unique key you are using to identify that row. While for your secondary index, you can use other columns. For example, you can use the age or, whatever. That is for secondary index. Now, remember that at the leaf page, we have both the key and the value, right? So this means that if we have multiple indexes, you will be duplicating the keys and the value, right? Basically, in the leaf page, right? And this can waste space, right? Because, I mean, why are you doing this? You are just duplicating all these leaf pages across all the indexes. So what can you do, right? So you can have a single file. This is known as the heap file in database, actually. And the heap file will be the source of truth for all the values, right? And what you can do is to store the offset, or basically the position of those keys in the leaf page. So you're not storing the value, you are storing the sort of like the position of that particular value in the leaf page, right? Which is sort of like lesser in space, like it's going to consume less space, basically. And so if you're familiar with pass by value, pass by reference, something that this should be clear to you actually. So that is for that. This is how that particular issue is handled. But there is actually a challenge for this, and the challenge here is that you are making a disk I/O each time you want to read a value, right? And so because this particular file exists in the hard disk, and if you understand how the hard disk works, basically you'll be spinning the disk, finding the sector, finding the block, and all those kind of things just takes time to, right? So what you can do is to store the most important columns in the leaf page, and then the less important ones, you can store them in the heap file, right? So you can store the metadata or something in the heap file, but the most important ones can be stored in the leaf page, right? So this is sort of like we trying to merge the two solutions together, right? So that's on optimizing space for B-trees, right? So that's my talk. Thank you very much. You can find me on Instagram, GiftedDL. You can find me on Twitter, GiftedDL, and I'm also on LinkedIn, right? So I think I'm open now to questions. In case you have any question, I can answer you.
Or just reading from listening to you. That was really clear. I'm looking at the Q&A section. I don't know if you can see it, but someone has a question. Any idea on how B-tree storage engines can be effectively managing concurrent and multi-threaded environments, and what locking mechanisms are commonly used to ensure data integrity?
Okay, so when you're using a B-tree, basically, that means you can have something called, if you use MySQL, there's something called the isolation level, right? And the isolation level is the way you sort of specify how you want a memory to be addressed when you are updating that memory. So for example, if I'm updating a key in database, if I don't want any other thread to mutate that particular key, I can say that, okay, there is actually a setting called isolation level. You can set it, right? So you want to make sure that you are locking that memory while you are performing an update on it, or while you're writing to it, right? You want to make sure you are locking it. So that is how you can that's how you can use B-tree in concurrent applications. Just check out isolation level. This will be very clear to you, okay? Yeah.
Okay, that's currently the only question now. I have a question actually. Also around the B-tree storage engines. You talked about key ranges and going down the key ranges to find particular keys you're looking for. I'm guessing these key ranges aren't fixed, and I was wondering, like, is there an impact of having a smaller or a larger key range on performance?
Actually, it depends on, you can actually specify the levels of the layers you want to have, right? And that is what really makes the impact, right? So if you have like the smaller your the ranges you're trying to scan, the faster, right? So it
Mm-hmm.
just boils down to the trade-offs you want to make, basically. So it just boils down to the trade-off, right? If you want to have something faster, then you have to have like lots of ranges, like a single page has lots of keys sorted, right? Otherwise, you can make it layered. And I hope that that is sort of clear.
Okay, yeah, that helps. Someone's asking, where can I learn all these? Is there a book or a course? I hear you talking about,
Okay.
different data structures, based on the title of your course, data transversal, merge sorts, there. Basically, someone's asking, where can I learn all of these? And I guess not just the data structures, but also how to learn about their applications to these different databases.
Okay. So if you want to read a book, I have some recommendations, basically. So there is this book called Database Internals by Alex Petrov. It's a very, very important book, actually. You can read that particular book. You can read High Performance High Performance SQL by, I've forgotten the author, but it's a very interesting book also. And finally, you can read Designing Data Intensive Application, right? So, I mean, that is the Bible of anything distributed systems or database, in my opinion. So you can read, designing data intensive applications.
Okay, I think that much is answered. Someone says, does the key range in B tree map to the table IDs?
Okay, so the key doesn't map to the table ID, right? So the key can actually be okay. So can I get the question again? I want to be very sure I'm answering the right question. Can you come again?
He says, does the range keys in B tree map? Sorry, does the range keys in B tree map to table IDs to the table IDs?
Okay.
I guess it's not clear. Is it clear
Yeah.
what he means by table IDs?
Yes, actually, so the key can actually be the table ID. So basically, you have the table ID mapped to the columns of that particular table of that particular row.
Mm.
So it can be the table ID. It can also be another column. You can use maybe the age or whatever, right? So that's just basically that's it.
Okay. Okay. Checking the chat for any more questions. None so far. Yeah, I think we can just hang around just in case there's someone who still has something to talk to ask.
Okay. 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 So the second book is I mentioned designing data intensive application. I mentioned database internals, and I mentioned high performance SQL. So those are like the three books I would recommend.
Okay, I guess the papers too. The papers you talked about a paper in your talk. So,
Yeah.
but
Okay.
we'll have the
So I
slide
think I'm
available after,
well.
so
Okay.
people can go through them
Yeah.
to. But you could also mention
Yeah.
it just in case.
Mm. Okay. You can check the ubiquitous B-tree. Then you can also check log structured match tree paper by O'Neill. So those are like the two papers that
Okay.
I specified. Yeah. Okay. All right. Thanks. Any more questions before I exit?
Yeah, I don't see any more questions, so I think it's okay if we leave it at that. Thank you very much. This was really informative.
Yeah. Okay. Thanks. Bye, everyone.
All right, bye.
Yeah.